Hello, everyone. Welcome to a new episode of our Oil and Gas Expert Series. My name is Alan Murgis. I'm a consulting reservoir engineer here in Australia, and I'm also the founder of CrowdField, a digital hub for subsurface professionals. The title of today's presentation is Beyond Correlations and Analogues, from sparse data to robust simulation inputs. And my guest today is Peter Kirkham, Project Services Manager at Twinza Oil. Peter is a petroleum engineer with broad technical and commercial oil and gas experience. He started out Novos Petroleum as commercial assistant to the CEO. He's worked across reservoir, wells, legal, commercial, and project development disciplines. He's currently the Project Services Manager for the Pasca project, PNG's first offshore oil and gas development, and he's the creator of the free Pyrus oil and gas tools software suite. So it's my pleasure to welcome Peter and share his experience with all of us today. Before handing over to Peter, just a bit of housekeeping. We have about 45 minutes for the talk, followed by some 15 minutes Q&A. Please, guys, stay muted throughout the session to reduce the noise. If you have a question, just raise your hand with the little hand icon you see at the bottom of the screen and wait for my cue before unmuting yourselves, or simply type your question in the chat. Now, this session is being recorded for later distribution.
Very good. So everyone should now be able to see my screen. Thanks very much for the opportunity to present this, Alan. I'm going to start off just by sort of introducing myself a bit and why I'm doing this. I work at a small oil and gas company called Twinza Oil. We're developing the Pasca field, as Alan mentioned, which is hopefully the first offshore oil and gas field development in Papua New Guinea. And one of the interesting things about this field is it's a carbonate Miocene reef. It was first discovered in the late 1960s. It's had 3 wells drilled on it. And all the wells that have been drilled experience huge losses, which has huge issues with the logging tools. Makes it very difficult to interpret conventional LWD or wireline. And so we had a lot of challenges working out how we're going to sort of model this field, etc. And as you'll find out separately in my free time, I have a bit of a hobby writing oil and gas software. So I've sort of brought the two together, and it's led to Pyrus. But the main thing is, in my day-to-day job, you can see I'm Project Services Manager, which doesn't sound very technical. It's, dollars and dates, making sure that the project is on time and on budget. But I am actually a petroleum engineer by background. Studied engineering at Cambridge University in the UK in the late 1990s, and certainly reservoir engineering is my passion. Essentially, Pyrus is a way that I get to keep my hand in and keep sharp on the technical front. That's what I'm going to share with you today. This is a free oil and gas suite.
Peter, just your camera is off, so you're welcome to turn it on if you want, but just so you know.
Oh, okay.
And it's off now.
How do I do that? I can do that, I think. How's that?
That's it. Now we can.
Okay. Now you can see me. So thanks, Alan. A little bit of history. It's a bit of a weird slide. I know programming is a hobby. Look, I started programming when I was probably about 11 years old. I found this image on the internet, the Microprocessor 3. This was actually the first computer that we had at home. My dad got it. It runs a dual processor 6502 and a Z80. And if you know anything about those chips, you'll be able to date me pretty well. It basically comes from the 1980s. And look, I mean, back in those days, the way you learned to program was, you'd have magazines and you'd copy out programs in BASIC to play various games, or you'd read all the manuals and you'd learn how to do that. You basically had to be hands-on. There was very little available just straight out of the box. And that sort of ethos has carried on with me into my adult life. And obviously I've transitioned from writing games to now oil and gas software tools. And there's a picture of my the desk I'm sitting at during the day. And the computer there is actually built that myself. It's got water cooling systems, big screens. I'm an absolute nerd when it comes to the computing. But the main point I want to make about this is that what I found is that writing the own software, it's obviously very rewarding, but actually you really learn a lot about petroleum engineering along the way. And I think Alan, has a lot of things that he's doing with AI and various tools that he does. And I'm sure, Alan, you find exactly the same thing. Doing it is the best way to learn. However, I have got something that I prepared earlier, and that, of course, is the Pyrus suite. So one of the first things he says, well, how do you actually get hold of the Pyrus suite? So what I was going to do is open up my browser here, and this, of course, is Alan's CrowdField website. And Alan's, interestingly, he's got a whole bunch of resources on here, various tutorials, but he does actually have down in this part of the page, he's got various open source tools that are available that you can use. And interestingly, he's featured Pyrus down here, which is great. Now, technically, not actually open source, which he does say here, not open source, but in here there is a link to my website. So if I click on here, what you find is we come to my blog, Pyrus, and various different links where you can download it. Thing I would highlight is that, look, this is not commercial software. Distributing software is actually quite a challenge. Package it, there's all sorts of different architectures out there. What I've done is I've created what's called zip, portable zip versions of the software. So we have it for Windows, Linux, two different architectures for Mac, whether you're on the old Intel or the newer Mac, M1, M2, etc. They're called ARM architectures. And you can download those. Now, if you download it and unzip it, what you'll end up is with a folder much like this one. I wonder if I can zoom in and make it a bit bigger so you can see. And you unzip it, it's got a whole bunch of folders. You'll be like, what the heck's this? This looks so unprofessional. But the beauty of this is you don't actually need an installer. All you need to do is go to the bin folder, and there's your executable. Now, on Linux and Mac, you might have to do a little bit of jumping through some hoops, which is explained on my website. But it basically opens up a conventional desktop application, such that you can see here. Now, why did I create this? Let me come back to my slides and go through to the next one. Where did this all come from? Well, I graduated in 1999, and the oil industry was kind of in one of our low points in that year. I think oil got down to $10, and it was very hard to go and find a job. Now, for my sins, both my parents are actually geophysicists, and my dad at that time was running I call it a cottage industry business from home, which is to do with seismic scanning, whereby you take a seismic section that had been printed out in with wiggle traces like you see here in the middle, and they would scan that in. And he'd written an algorithm originally in Fortran that would essentially reconstruct these traces into seg-y format, so a digital format which you can then open in a computer and view, etc. So in 1999, while I was looking for a petroleum engineering job, I was helping my dad doing various programming jobs for him. And one of the things I started to do was actually port that Fortran code into Java. In the late 1990s, Java was a really new, interesting language. But it was also one of necessity to some extent, because I was writing in Windows, and all the high-powered computers in those days, they were running on Solaris, which of course is Unix. And the great thing about Java is it would run on both of those computers. What you're going to see is that Pyrus has, it's a bit of a hodgepodge of different tools. But the original seismic reconstruction tool is still embedded into Pyrus. And I thought I'd just show that, first of all, just as a bit of interest, to show you sort of thing that we can do here. So what I've got here, I've obviously set up a project already, and you can see here is a a 2D seismic line that's been scanned in. We have a little navigation window here. Now, the thing is, how do we get this into SegWi format? As I say, there's a lot of things I learned through doing this. And essentially, if I run through the process and you see some magic things with images here, first thing we can do is we've got to actually capture the main area that's in the point. So if I digitize my points, you can probably just see there's a light green area around here. I've obviously set this up earlier. And what we can do is hit that align button. And before you know it, there you go. What it's done is it's cropped out all the parts of that image except for just the seismic. We can then do things like remove the timing lines, come through to another section here, run that, and off you go. You can see magically timing lines have been removed. And the way this algorithm works is it's actually going to look at the peaks as you come down. So if I zoom in, so you can just see the peaks and the individual pixels a little more carefully. We can also remove the traces. So we do that, and poof, off they go. And what this allows us to then do is run the algorithm, which my father had created, and create a SegWi file. Now, I'm not actually going to go and run that. I'm just going to open up the image that you see, and you go, oh, that's a little interesting. Not sure how good that is. Let's open up the original image that's been cropped, which I will show you. Hopefully opens up here. Oh, there we go. I thought it crashed for a moment. Now, one of the great things about Pyrus is this is actually built on another wonderful piece of open source software called NetBeans platform. So all this windowing stuff is all built in, allows us to do some nice fancy things. Now, what you can see straight away is that kind of looks sort of similar to the two. We do some additional processing to bring out the amplitudes. If I open up the amplitude window, come on, double click, open up, there we go. And I can also open up a slightly cleaned up one. We can apply different color palettes, and you can sort of start to see the similarity between those two there, which is nice. If I zoom in a little bit to both of them and switch this to turn off the legend and use a wiggle trace plot, you can sort of see how that works. And look, this was, as I say, started writing this in the late 1990s. And you can imagine there was probably quite a lot of, well, there is a lot of underlying software. This Pyrus has been going on for a long while, but I've never released it. Essentially, the foundation is built in all these kind of tools in here. So let's close all that down, and let's come back to some petroleum engineering, which is where I want to go next. So there's my slideshow. Here we go. So 2020, fast forward, I've been playing around with Pyrus for a long time. I've had a whole host of, shall we say, everyone has their sort of bottom drawer of oil and gas tools, a lot of Excel tools. In my case, I had quite a few little sort of Java command line tools, etc. Things that I use day to day just to help me with various calculations, manipulating data, etc. But the real big thing, the change that came for Pyrus came with COVID in 2020. And I found myself having to, for the first time, really actually get my hands on into editing and working with the simulation decks for the Pasca field in Papua New Guinea. And one of the first things as a programmer I thought is, why is there no integrated development environment for Eclipse files? Like, surely this is a really obvious, easy thing to do. Now, some of you may come across integrated development environments. There's things like VS Code or IntelliJ and PyCharm and all these sorts of things. But essentially what it is it helps you as a tool to work with your programming language. And essentially a reservoir simulation deck is essentially, it's a language. It's saying that this is what I want you to do to run the simulation. And all the keywords have a certain structure to them. And we should be able to use that and leverage that to make it easier for us to edit these decks and use them. And obviously in COVID, I had a bit of time on my hands and actually started writing my own reservoir simulator as well, which I haven't released yet, but I mean, it's all in the works. But what I'm going to show you is what I think is one of the more useful tools in Pyrus that sort of goes a little bit under the radar. So here we have, I've taken one of the SP3 cases. So this is the SP Comparative Solutions project. There's two ways you can open this file. You can either come into open file and navigate through to put it on my desktop and open it this way, and you'll see it opens in a sort of text editor, and you can see straight away that the the keywords are all nicely colored, etc. Alternatively, you can literally just drag and drop it in and up it opens, which I think is quite a nice little thing. Now, this is going to be a little bit hard to see in this particular color scheme. This is the default color scheme that comes in Pyrus. It's based on the, as I say, the underlying open source software, NetBeans. I've been using a different color scheme for a long time, so I'm just going to quickly change that. One of the things I do is I set the right margin to 120 characters wide, because that's how wide I like my decks. And I also need to change the colors to one called Norway Today. I'll apply that, and you can see that there. And one of the small bugs with this, and it's from the underlying software, is it still retains the caret, which is black from the previous case. So, but if you do, all you have to do is close it, reopen it, and now it comes up in a nice, easier to see yellow. So what can we do in this? Obviously, you can see here's a deck. I just scroll down. One of the first things you note is it has syntax highlighting, and all the keywords here have a particular meaning. So your main sections come in a, to try and make it even bigger and easier to see, come in a kind of, what do you call it, magenta. The keywords themselves come in red, numbers are in yellow, strings are in white, comments in blue, etc. And the thing is, this is constantly reading everything that's in here. It has error detection built in. So if I had a keyword that didn't make sense, for example, if I change that to, oh, shit, it didn't work. There you go. If I put in a keyword that's nonsense, you'll see that is actually, and hover over it. It might be a bit hard to read, but it says keyword DXRFS is not a valid keyword in the grid section. Well, of course not. So let's put that back. Over here on the left, we have a little navigator. I can open all of those keywords and it shows me all of the keywords that I have in my deck. I can navigate to any one of them just by double clicking on them. So if I want to come down to the schedule section, oops, I closed that, and say RPTST, come down here, and there we go. It's navigated caret straight to that schedule section at the end. So that's quite a useful thing, especially if you're a consultant or someone and you're quite often getting decks that you've never seen before. This is an immensely useful tool. Another useful thing here is that because the IDE is aware of all the keywords, you might be able to see on the left here, there's a little folding icon. We call this code folding. So if I click on that, that collapses the tab dims, or click it again and expands it. I can do the same with equal dims, and so on and so forth. If you want to do all of them, I can actually do Control-Shift-, and that's now collapsed every single keyword in the entire deck. So if I scroll out, you can now quickly get an overview of your entire deck at a glance. Again, very useful if you're just trying to navigate around the deck and see where things are. You want to expand them again, Control-Shift+. There is actually in here, built into the tools, options, key map, it does actually tell you what all the shortcuts are, but I won't go through them all individually. The other great thing about this, as I say, it's built on the NetBeans platform, so it's actually got a bunch of very useful text editing tools built in. If you want to use, for example, I'm trying to remember what they call it. There's a special way of editing so that you can do it column-like editing. Control-Shift-R, that means I can now come down here and, for example, just do -- to comment out all those lines. It added a dash to every single line. Or if I just want to delete them on the first 3, select down there, delete those. Do the same for that, which is very useful, particularly if you're editing, say, down in like dates down here, and for whatever reason, it's a bit of a silly example, but say you wanted to change all those 28s to 30, you can select them in a rectangular block and just type 30, and off you go. Bob's your uncle. Of course, we have undo and everything, so I can undo that, turn them back to 28, and off we go. What else can we do in here? Well, one of the big things is that when you get a deck, quite often it can be a bit of a dog's breakfast. Now, these ones come from the OPM project. They're not too bad, but again, I mean, you can see here, for example, the well injection constraint. I mean, it's listed here, item 1, 2, 3, 4, 5, 6, 7. Like, okay, great. I can't remember what those are off the top of my head. Okay, no worries. I could add title and info. So I right-click on the keyword, and that's going to add in a comment above telling me actually what all those keywords are. Okay, that's kind of useful. What else could I do? I'm just going to delete that and press Control-E, get rid of all that. I have this wonderful little tool here called the Eclipse Language Manual. Now, I've actually gone through and taken pretty much the entire OPM flow manual and put it in here as well. Now, this might be a bit hard to read because of my screen resolution, so I do apologize for that. But it does have this thing up here called Sync Caret. If I now move my cursor and click into wcomprod, it will bring up the manual for that keyword. It's got every single description of what you need here. It describes the difference between the different units. And unlike a PDF manual, let's say you're reading through this and it's got the hyperlinks through to, here you go into something by VFP prod. Okay, I can go to that. Now in a manual I might go there, but oh, now I want to go back. Well, just like a browser, you can go back. And this is incredibly useful when you're looking at the deck and just trying to work out what's going on. But wait, there's more. We can format our keywords into a consistent format very easily. If I select that keyword and press Alt-Shift-F, bang, that just formats perfectly compared to, you can see here, well name type status, exactly how these are named here. Now, except these names come from OPM flow, but I say it's very, very useful. I can actually, just without even selecting everything, I've tried to, I hope this doesn't crash, Alt-Shift-F on the entire deck. That has now formatted this entire deck to the Pyrus standard. Again, very, very useful. And the only snag, so if I Control Z, is to show you is that what it does do is if there's comments within a keyword, so let's take this equil keyword here, for example, it's going to kill those and replace it with its own heading. So for example, if I just select that and hit Alt-Shift-F, it got rid of all those keywords and replaced it with its own. And in this case, that's probably not too bad because, well, it's kind of saying the same thing, just more compactly. But if you did want to keep it, some very interesting tips, you can do Alt-Shift-Up, and that moves everything up in your block, one line. Alt-Shift-Down. If you wanted to copy something, you can do Control-Shift up and down. So for example, if I come down to the end where I have a bunch of years, let's say I want to add another year to my time steps, Control-Shift-Down, that just literally duplicated the line below. As I say, there's a lot of these tools and tips and tricks in the language, in the integrated development environment. To find them, the best thing would be to come over to Pyrus. If we go to the features and look into the Eclipse language editor, I do sort of describe them here, everything that can be done, such as editing assistance comes down and it gives you some of the bookmarks. I haven't even mentioned you can do bookmarks, quick reference for all the shortcut keys that you can use. I mean, essentially, this is a text editor on steroids designed for the Eclipse language. To be honest, since I made it, I can't really live without it. It is that useful. I think that probably covers most of the IDE. I'm just going to check if there's a. Oh yes, one thing I wanted to show was the linting. So linting, for those that don't know, is sort of something that gives you hints about your code, etc. Now I've only really just started doing this, but let's say for whatever reason I had field and I'd also got metric in the same deck. Hopefully you can see here what this has done is it's put a little icon here. You can see it on the side here. There's a bit of yellow. There's some yellow here. And what it says is a conflicting system of units definition. Alt-Enter shows hint. So you press Alt-Enter. It says, do you want to remove the conflicting system of units? Yes, please. Remove you. And it gets rid of metric. Everything is back to normal again. Thank you very much. So as I say, that's somewhere where this is going. And hopefully you can see the power of an integrated development environment. With that in mind, where to next? I think when I started putting together the decks, and look, I mean, Twinza, we've been bootstrapped for pretty much, over 10 years while we were trying to get our project approved by the government, and it is now, and it's moving ahead, which is great. But in those previous 10 years, budgets, cash were often quite constrained. We did enjoy the wonderful ability to use T-Navigator for a while, and I love that. That was a breath of fresh air compared to Eclipse. Your mileage may vary. I don't want to cast aspersions against any one of those, but when we ran out of money, had to go to, I ended up picking up OPM Flow, and I should just say one of the reasons I did that, and one of the reasons why this manual is in here, shout out to a chap called David Baxendale, who was a consultant in Singapore, used to work for RPS Energy before they closed their Singapore office, and unfortunately he's passed away now, but he was the original writer of the OPM Flow manual, and he encouraged me to get involved with that and to use OPM Flow for reservoir simulation. And so certainly for a period of years we did that, and so I've been contributing small changes and fixes to the OPM Flow manual, which I come across as I've been putting it here into Pyrus. Now, what I've found is that's all well and good. We can get our deck, but I need to come up with some keywords. Now, we had a geologist who was making the grid in a patrol model and everything. That's fine. But as an engineer, I'm going to need fluid properties. So that's my PVTO and PVTG tables. I'm going to need saturation tables, etc. So I'm now going to show you very quickly how we can create those. So if I close this down, oh, I didn't mean to do that. Come back to my PowerPoint, PVT input. So what we have, when I see PVT, we can usually have lab results. We take them, put them in. The key thing is, how do we characterize the C7 plus fraction? And I have a way of doing that in Pyrus that basically links your molecular weight, your specific gravity, your single carbon number, and your paraffin, naphthene, and aromatic components. You can see here, these all have 6 carbon molecules. There's a relationship between them. Won't go into the details, but you're probably all familiar with Katsburuzabadi. I ran Pyrus on it. And essentially, this is how the PNA distribution varies for Katsburuzabadi components. Now, if I come to Pyrus itself and open up, create a fluid window, what we have here is a way that we can enter in classic distributions. Now, just looking at time, I need to start moving a bit faster. Let's say we had a simple fluid with some just methane through to pentane, also to butane. You can see that creates a classic phase envelope. This is using just a basic cubic equation of state, which is the Peng-Robinson cubic equation of state. If you're trying to do this by hand yourself or in a spreadsheet, it can get kind of involved. There is specialist software to do it, but of course that costs money. There are certainly free programs that you can use, certainly Python libraries. Nexim from Equinor is another one that does this. But I do believe the C7 Plus characterization in here is kind of unique and something that gives it a little bit of an edge. What I'm going to do now is I'm just going to close this. You can see I've got an Excel spreadsheet open here and close my Eclipse manual. Because what I wanted to show you is rather than typing in everything by hand, if you had saved stuff, you can see here, I'll start with the Volve composition, CO2, nitrogen, CH4, etc. You can actually just Control-C and import. And off we go. That's now Peng-Robinson phase envelope for that composition. You can see 43.428. That pretty much matches the carbon there. Now, we know the bubble point of this as well. I'm just going to change these axes to a fixed scale as well. We've got all sorts of units here that we can use. Volve, obviously, Equinor, they love Celsius and bars. Make that 550 down to 0. Put that up to 350. Now, if I enter the dew point of this, 106 and 273.2, and plot that on here by ticking on the reservoir condition, you can see that the initial Peng-Robinson is absolutely miles off. Well, don't worry. We got some other equations of state in here, including one called the enhanced predictive Peng-Robinson, which is one of the more modern equations of state. We can select that one and it recalculates, and you can see that gets a little bit closer. Again, on my blog, I have things explaining how we apply this to the C7 Plus, which is not straightforward. But best practice, my friends at Whitson, Marcus Hayes Nielsen would always tell we should be splitting the C7 Plus fraction. We can do that by clicking that. We use a gamma distribution to do that, and you can change the parameters to do that for tuning it here. But again, for the moment, let's just come back and have a look in here and see what happens. And you can see that expands a little bit more. Now, if you can see here that the actual input, and this comes from the lab analysis that was done for Volve, has a very low aromatic content. If I was to use Katz for Ruzabadi instead, by just clicking Katz for Ruzabadi, changes the PNA, and again, that's changed the phase envelope again. I happen to know that it's 35.2 based on the assay. So if I put that in and see what happens, fingers crossed, we're now starting to get exceptionally close to that number. At which point you can say, okay, that's not too bad. That's pretty interesting. We can start to tune things as well. If I change this to, well, I don't know, I can't remember what the right numbers are, but let's just put in a few numbers, tune the gamma distribution as a split, just an example. And you can see, oh, look, pretty much lines up. Now, you can obviously do a lot better and go from there. We can also do other things, looking if you want to compare it to lab data. If I reset this, get rid of that point there, I'll show you, this is the Pasca data, so I cut and paste him in instead. And again, I think I'm set up with, the enhanced Peng-Robinson. We'll use the split again. I like to think in Fahrenheit and PSIA. Actually, I need to set up this to PSIG because our dew point is 3060. So now, one of the things you notice, I set this to PSIG and put in 360. If I change that back to PSIA, it automatically converts every single number elsewhere in here, which is kind of neat. If I just do a fit, you can see that's what the phase envelope looks like. Now, when I was looking at this, sometimes you want to see where's the critical point. We can do that here with just clicking on there. You might also want to see, well, okay, that's great. That's, where am I liquid and gas? I have a little thing called a heat map that you can click on, for example, and do that. And it colors in red for all gas, green for all liquid. And you can start to see your how your phase envelope is changing all the within that. I can put a surface condition on here. It's just default, but if I hover over that, it shows me what fraction I have. So here it's 88.2% vapor. And if I click and move that somewhere else, you can see that it moves. If I click, it actually moves as I move it around. So that's a useful, nice little tool as well. You might have some lab data that you want to calibrate your points to. So this one happens to have some lab data at 240 degrees C. I can cut and paste him in there and then see what kind of match I'm getting against there. And you can see straight away, actually, that's interesting. That's not coming out too bad at all. I happen to know that if I change that to 0.67, it gets a lot better. And if we look on the phase envelope and plot our reservoir condition on here, fingers crossed, you can see that cuts through quite nicely. Now, I mentioned before, what if you don't have very much, you want to create your PVTO from that, you can come to your simulator export, and I can actually calculate consistent PVTO and PVTG field units, click on generate simulator words, and there you go. It's created those black oil tables using compositional flash for all the points, which you can then, of course, just cut and paste into another deck like this. But in the interest of time, I'm just going to move on. I did say the whole point of this talk is, what if you don't have very much data at all? Particularly you haven't got lab data yet. So, I did ask myself a while ago, surely we should be able to estimate this thing. If I could just guess my composition, guess the methane, inerts, ethane, etc. And I know my field data. It's very common, separated data. You will measure API, gas gravity, gas oil ratio, and your separated pressures. Can we match that? So if I just quickly put in into here a very quick transposition of that. 60. No, I'm not going to click go yet because I'm just going to quickly come back to explain how I do this. I'm not sure if anyone's come across genetic algorithms before, but basically we all know about people, life. We have genes, we have parents. When they breed or mate, what happens is their chromosomes get crossed over. So if we actually define our composition using a range of numbers, you can imagine X1 is the methane percentage, X2 is the ethane percentage, etc. We breed two particular candidates in a population, cross over their genes, you might get some mutation, put them in. We can then do a flash on these children, and we can compare their API, gas gravity, and gas oil ratio to our target. Are they close? Get closer and closer. That's how a genetic algorithm works. It evolves towards the correct solution. Now, the really interesting thing is if you actually calculate how many different permutations are there, if you wanted to brute force it, I think it's something like 3 times 10 to the 17 with just integer percentages. I mean, it is an insane number of permutations. I mean, the chances of winning a lottery, if you pick one in six numbers between 1 and 47, I think it's like a 1 in 3 million chance or something. You're I think 30 billion times more likely to win the lottery than pick the right number here. So, how likely are we to actually get something that works? Well, if I just click on estimate here, you can see it's thinking down here, bang, it's calculated a number. I can export that. I'll come back to my composition over here, phase envelope, reset him, turn off my heat maps and everything. And I will now import him. And what you can see is he's going to create a nice little phase envelope. Fantastic. As I said before, I like the enhanced Peng-Robinson and split function. We'll keep using that. we know this is some data I got from a textbook. The dew point is 240, sorry, bubble point, 250 degrees F, 2392 psi A. We'll plot him on there. Gosh, I wonder how, like, oh, look at that. That came up pretty well. Now, I did actually put that on a LinkedIn post the other day, and some people might go, oh, that's a bit of a fluke. So we can try another one. So let's put in 40.7. API 0.855. This is the thing. It doesn't come up exactly the same each time. Sometimes it's a little bit off. I'll show you how we can get around that in a moment. If I hit estimate on him, he's going to come up now with a new composition. Export him, import him. Now he plots up in me. Now you can see that's the old point. So what's our new point? We're 220 and 2635. Let that replot. And that's pretty close, not too bad. Now, as I say, it does vary a bit. So I have a Monte Carlo technique that you can use. If I do 25 runs of that, now it's going to take a little bit of time to go through. Or maybe it won't. If you want to see its progress, you can come down here and it gives you some indication of what it's doing. It's on iteration 7 out of 25, 8 out of 25. It's coming up. That'll come through. Well, let's let that run. And while that's running, let's move on to the next section, which is pipe flow. Now, look, I mean, fluids is one thing. I find it astonishing that, you know, over a century since Van der Waals came up with the cubic equation of state, we still don't have a perfect solution to that. Multi-phase pipe flow is another very challenging issue. And recently I came across a thing called fractional flow theory by Dr. Nagu in the US. Now, usually what we do is we look at something like a critical velocity for our multi-phase flow, which is the velocity at which we might expect droplets to be held up in annular flow, and we can plot a flow map for different times of flow regimes, run through a whole bunch of equations, and if I plot then my gas void fraction, which is essentially how much gas versus liquid I have versus the fractional flow of gas, I come up with this dashed gray line here using classical traditional methods. There are certainly some people I've been talking on LinkedIn, they always point out that, you know, go back to data. That's exactly what Dr. Nagu has done. And his pipe fractional flow theory, this is from one of his papers, you can see matches some published data quite well. I brought that into Pyrus, and you can see that that's pretty much the same shape, which is great. So we've brought that in. We then also need to model our well so that we can model the heat transfer. Again, this is immensely complicated. You know, you've got cement, you've got different pipe thicknesses, etc. You've got conduction, you've got convection of the actual fluid up the well, you've got joule dumps and cooling, you've got kinetic energy changes. There's a lot going on, and this looks like full on. I'm not going to go through it, but essentially this is the logic encoded in Pyrus for how I calculate pressure and temperature changes from what you just saw, the compositional gas and oil and some water going in. We flash those and essentially get our flowing vapor and liquid. Now, whilst I was explaining all that, let's come back to Pyrus. Our Monte Carlo simulation is run. We'll export him, import him, see if we get a better result. Probably not. He's about the same. As I say, it's when you consider what you're doing here, I think the fact that this comes out this close is pretty amazing. I've been testing it against lots of existing correlation, Beggs and Brill, Ballard, even some artificial neural networks and stuff. And generally, so far, this is coming out better. But this is still sort of hot off the press. What I want to go on to next is, so coming back to this wellbore, multi-phase flow, is just introduce very quickly another tool, and then I think we'll probably come up to time, won't we, Alan? What I'll show you here is basically how I have created a quick, this is modeling for wellbores. So just to make it easy, I've just made a reminder for myself of some numbers I need to put in here. This is for actually a well that Twinza drilled offshore in Papua New Guinea called Pasca A4. first thing we do is put in the geothermal gradient, a bit about its location. We need to put in a trajectory. This is just at the moment a vertical well, but we can come here, change this to deviated well. If I was to put in here some numbers related to a J-shaped well, like this, what have I got to do? Generate the trajectory. You can see, yes, this creates a trajectory for you, so you don't have to do the calculations. It comes MD, TVD, MD inclination, azimuth, offset Z, XYZ. All of these update automatically. I believe I can actually change the numbers in here, and it will change all these others updated dynamically as well. But let's not worry about that for the moment. If I've got an S trajectory instead with the same toe offset, I can click that and generate him instead. You can see that does a build, hold, drop. Fantastic. What if I've got a horizontal well instead? Okay, let's click that on. Put in 2,000 feet. Generate him. You can see that does like a horizontal trajectory. So that's kind of useful. Let's put in the Pasca one. So he comes in at 450. And he's got a 1.7 build-up rate, 7,600, 3,290. I am S trajectory and 6,900. Generate him. So that's pretty much the Pasca trajectory. Now we have to put in the actual well itself. So we come down. Next one is hole size. If I come to my schematic, you can see here it's automatically got some bit size. If I put in, let's say the first one for Pasca was 36 inch, 136, and went down, how do we go, 631.4. I can then update him, and you can see that there's a little schematic emerging here. Now, just to speed things up, we can also cut and paste in all these numbers. So let's do that. There's the hole sizes that I drilled. We can do the same with casing. It allows you to estimate inner dimensions and stuff based on the weight. Won't go into that for detail. I'm just going to show you that. Actually, therefore, it's plotting all the thicknesses to scale. We can put in some tubing as well. So I'll just quickly put that in. And there you go. That's essentially the Pasca well. It's an S shape. Right. Now, what can we do with this? One final thing. I need to put a completion in. 7464. So back to schematic. So there's my completion. Oh, that didn't look right. 7. Because I need to be MDRT, I think. Let's just bump him down a little bit. Let's leave him there. See if this works. I still have, I need to put my Pasca fluid in. Let's just create a fluid. Cut and paste my Pasca fluid in from before. Import him in. Make sure I'm on Spring Robinson split 0.67. Right. I can then use that mixture, and I can start to simulate my entire flow. Okay, here we come. Fingers crossed, third time lucky. Hey, here is a classic VLP lift curve. So if I show that on the chart here, and then I sort of come up here, you can see this is showing pressure and temperature up and down the wellbore as the rate increases up the well. So, you know, I think we actually got up to about 53 million scuffs a day on test. So we were around about there. Now, what's really interesting, if I should look at the pressure gradients, the blue line is the hydrostatic pressure gradient. The green line is the frictional pressure gradient. And we look back at the schematic, you can see there's actually a constriction down here at the bottom. And you can see in the VLP, that's actually leading to an increase in the frictional pressure gradient there. We can also look at how the fluid evolves in here. And you can see that blue and green are essentially the amount of liquid there is. It's pretty much zero. As I increase, you can see that it's gas. And as it comes up, you then start to get liquid condensation as the pressure and temperature go below the dew point. And if I, for example, come and have a look at my pressure and temperature, you can actually go where I'm about 6,100 there, where it starts to come out. 6,100, that's around about 3,000 psi at 190 degrees C. You can come back here, look on here, about 190 degrees C, and you'll see that that's around about that pressure, which is kind of interesting. So it all kind of works. It's all consistent, all ties together. There is more, but I think we kind of run out of time, haven't we, Alan? So I'm going to call it in. There's one final thing I wanted to show. If I go to the very end, is basically thank you to Alan, thank you to CrowdField. There's quite a bit more to Pyrus than that, but that's it from me for the moment, I think.
Thank you, Peter. I mean, this was absolutely incredible, man. Kudos to you. The products you've developed as a solo developer, it's absolutely amazing. The only question I have is, how didn't I come across this sooner? Every product here as a standalone product looks of immediate utility. So thank you very much for this walkthrough. It's better to hear from the creator directly rather than try it on your own in your spare time. So thank you very much for that. I think it's very interesting to understand also the philosophy. Everything serves the simulation deck. So starting from the simulation, and then the PVT that serves the simulation deck, then the pipe flow, whatever the name of that module is, serving also the simulation VLP table. So everything looks very coherent. And again,
yeah, absolutely, Alan. I mean, I wasn't sure how long this would take to present. I wasn't sure I was going to have enough to fill up the time. It's gone on for a lot longer. But yeah, you can export the VLP tables, so VFP prod, VFP eng, into the deck. I also have a relative permeability table generator as well, which uses, it's based on a permeability function that I sort of developed myself based on the Kozeny equation. But I think that's, yeah, at least another hour. So
did you mention, I think that the generic algorithm to back calculate the composition that
yeah,
that fits, test that's absolutely incredible. Did you mention that it's just hot off the press? Or did I hear you?
Yeah, I developed it about a year ago. It was kind of interesting. I played with generic algorithms with my dad for some geophysics processing about 20 years ago, and I really came to understand the power of them. It didn't actually take very long to write. That was the amazing thing. It just took like a few days. Tuning it and calibrating it and getting it to behave is a different story altogether. But really, yeah, it was just an idea. I just curious, and that a lot of Pyrus is just because I'm curious. How does it work? It turns out to be quite useful. The one thing, of course, is, with this, it's free software. I'm not a big company or anything like that. Getting it known and, I guess, accepted by other people is a far different challenge. But as I say, I'm not in this to
absolutely
at the moment make money. And I guess I should also say I've thought about this long and hard. People go, how are you going to monetize it and stuff? I have a plan down the road for stuff with the economics side of it, which I do a lot in my day job as well. But it's all underpinned by the technical stuff. And I've decided that will stay free for engineers that want to use it forever. It's my philosophy.
Wonderful. Absolutely amazing. There's a hand up. Take it away, mate.
Hey, Peter. Thanks, Alan. Thanks for the presentation. It was super good. I love this kind of small tools, and I think what you have done is it's incredible. Huh? So I want to say, and just one question: do you have like regular users who are using it in kind of their daily work, and they give you feedback?
Not really.
I have to read this. Maybe how do you grow on your ideas? So do you have like users coming back in and like, can you build this in? Can you do this?
Yeah. Look, I mean, as I say, I have a blog, which you can, if you go to CrowdField, and as I showed at the start, go to Pyrus, that'll take you to my blog. And on the About Me page, there's a contact form. Now, some people have used that and got in touch. I had a chap in Perth got in touch with me because he's looking at fluid compositions from exploration perspective, and I was able to help him use that to match some things that he'd been looking at, and he hadn't been able to get any matches at all using some of the other software he'd been using. We put it into Pyrus, and straight away, I think the real trick is the C7 plus characterization combined with the enhanced predictive Penn-Robinson, combined with splitting the C7 plus component using the gamma distribution. That seems to be the sweet spot to getting things to be almost, well, not 100% predictive, but pretty good first time off the bat. It's a little harder with gas condensates and volatile oils, but it can be done. And certainly I've got an animation somewhere on my LinkedIn I did just using a range of API, gas gravity, and GORs from dry gas all the way through to heavy oil. I created an animation showing how the phase envelope evolves using the composition, the genetic algorithm to create every single phase envelope. So it does work across the entire spectrum.
I'd be very happy to liaise with Peter to line up a follow-up session to see the rest of the product, which looks incredible. Kudos to you, mate. Fantastic product you developed. Amazing. Thank you, everyone, for coming in. And I'll see you on the next one.
Okay. Thank you very much for your time. And thank you, everyone, for watching. And everyone who watches in future, thank you very much.